Something unusual is happening around a distant star, and the universe has offered no easy explanation. The star is catalogued as KIC 84628552, but most people know it by a different name, Tabby's star. From the moment astronomers first examined its strange flickering, they realized they had encountered a phenomenon unlike anything seen in modern astronomy. The light dimmed by dramatic, unpredictable amounts. It behaved in ways that defied the standard rules of stellar physics. These signals created a puzzle so deep that even today, a decade after their discovery, scientists are still debating what is truly occurring more than 1,000 light-years away. This is the story of one of the most perplexing cosmic mysteries in the Milky Way, a mystery that forces us to confront the limits of our understanding of stars, planets, and possibly even our assumptions about life in the universe. The story began with data from the Kepler Space Telescope, a mission originally designed to hunt for exoplanets. Kepler watched more than 150,000 stars at once, measuring their brightness with extreme precision. When a planet crosses in front of its star, the light dips by a predictable amount. The pattern repeats, and the dip is small, usually less than 1%. That pattern is what astronomers expect to find when they search for new worlds. But when Kepler observed Tabby's star, the light curve made no sense. Instead of small, regular dips, the brightness plunged by as much as 22%. Nothing that large and opaque should be able to block a star so dramatically without revealing itself in other ways. The dimming was irregular, unpredictable, and far too extreme to be caused by any known planet. Kepler had recorded something that challenged basic expectations. This anomaly drew the attention of Tabitha Boyer-Gian, an astronomer whose work would eventually give the star its famous nickname. After she and her colleagues examined the data, they struggled to match it with conventional models. They ruled out many common explanations. A star-spot pattern could not account for the size or timing of the dips. Instrument error was unlikely, as multiple detectors recorded the same behavior. There was no evidence of a companion star or a giant object orbiting regularly. Every ordinary explanation fell short. The strangeness deepened when researchers analysed historical photographic plates from the late 19th and early 20th centuries. These images suggested that Tabby's star had been slowly dimming for more than a century. Although later studies debated the exact rate, the long-term fading introduced a new layer to the mystery. Not only did the star flicker, it seemed to be losing brightness over decades. That was not normal behavior for a star of its type. The scientific community began proposing theories to account for the extraordinary data. One of the earliest ideas involved a gigantic cloud of comets or debris passing in front of the star. This cloud would need to be immense and varied, causing irregular and deep dimming events. But the amount of material required would be extreme. Comets could not easily explain the long-term fading or the precise shapes of the dips. The hypothesis remained possible, yet unsatisfying. Another idea centered on the star itself. Perhaps internal changes were affecting its brightness. But Tabby's star is not the kind of star known to undergo large random fluctuations. Its classification as an F-type main sequence star suggested stable, steady output. No known mechanism inside such a star could produce dimming events of this scale and randomness without other clear signatures appearing in the data. Some astronomers explored the idea of large fragments of a disrupted planet. Perhaps a world broke apart under tidal forces, spreading debris across the system. This concept could account for irregular patterns, but it struggled to explain the century-long dimming. It also raised questions about why no heat signatures indicated the presence of warm dust, which should have formed from such destruction. Then came the theory that captured widespread public imagination, the possibility of a megastructure built by an advanced civilization. This idea was never the favoured scientific explanation, but it became part of the discussion because the data was so unusual. If a super-advanced species constructed enormous structures around their star, the structures could block significant amounts of light. The pattern might resemble what Kepler observed. This concept was framed as a thought experiment rather than a conclusion, yet it highlighted how extraordinary the star's behavior appeared. Researchers were careful to emphasize that extraordinary claims require extraordinary evidence. There was no proof supporting the existence of a megastructure. The idea was interesting, but speculative. Still, its presence in the scientific conversation underscored the difficulty of explaining the mystery through natural processes alone. As new observations accumulated, astronomers searched for clues. Multi-wavelength measurements offered critical information. If large amounts of dust were responsible for the dimming, different wavelengths would reveal different depths of blockage. Observations did indicate that shorter wavelengths dimmed more than longer wavelengths during certain events. This pattern was more consistent with dust than with solid, opaque objects. Dust, however, came with its own challenges. Dust should produce heat, detectable in the infrared. But Tabby's star lacked the strong infrared signature expected from large clouds of warm particles. The debate intensified. Some researchers proposed that the dust could be unusually fine or unusually cold, perhaps originating from disrupted objects far from the star. This dust could drift inward over time, creating both irregular dimming and long-term fading. Yet the details remained difficult to match precisely. The distribution, temperature, and behavior of the dust needed to be incredibly specific. As the scientific investigation progressed, public interest grew. Tabby's star became a symbol of scientific curiosity and the desire to understand the unknown. It stood as a reminder that even in a galaxy filled with billions of stars, some still behave in ways that push the boundaries of established knowledge. If you enjoy stories like this, consider subscribing for more. The search for answers expanded through citizen science. Volunteers around the world helped analyze Kepler data, looking for patterns that automated systems might miss. Ground-based observatories conducted follow-up studies, monitoring the star for new dimming events. In 2017 and 2018, fresh dips occurred, allowing scientists to gather new data with modern instruments. These observations strengthened the dust-based explanations. The wavelength-dependent dimming seemed consistent with fine particles. This nudged the scientific consensus toward natural processes. Despite progress, significant questions remain. If dust is responsible, where does it come from? How is it replenished? Why does it appear in such unusual distributions? A stable planetary system should not produce constant waves of fine dust without signs of catastrophic events. Yet there is limited evidence of such events around Tabby's star. Some researchers suggested that a swarm of objects in highly eccentric orbits could release dust during close approaches. These objects might be remnants of a disrupted moon or planet. Over time, their fragments could continue to shed material. This concept could potentially explain both short-term dips and long-term fading, but confirming it requires more observational data. Others proposed that the star's environment may be responsible. Perhaps interstellar clouds or filaments of gas and dust pass between Earth and the star. If these clouds are exceptionally thin or uneven, they could cause intermittent dimming without leaving strong infrared signatures. Yet these clouds would need to align perfectly with the star's position and appear in no other nearby systems. The scenario is possible, but demands rare circumstances. More recent studies have focused on the star's intrinsic properties. Some models explore the idea of a star that ingested a large planet in the distant past. This event could have disturbed its internal structure. As the star relaxes over time, subtle fluctuations might manifest as temporary dimming. But the extreme depths of the dips challenge this explanation. No documented stellar ingestion event has produced dimming patterns similar to those observed here. Despite long debates, the mystery has not faded from scientific interest. Tabby's star represents a case where data outpaces theory. It is a reminder that anomalies drive progress. Each failed hypothesis pushes researchers toward more refined models. Each new observation eliminates another unlikely scenario. The process is slow, but it is also the heart of scientific discovery. The star has a place in the broader story of exoplanet research. Kepler revealed thousands of worlds and countless stellar behaviors. Among this vast dataset, only Tabby's star displayed such extreme and unpredictable dimming. Its uniqueness gives it significance. Something rare is happening, and rare events often teach the most. Continued studies rely on coordinated efforts across multiple observatories. Astronomers monitor brightness levels and watch for new dips. Instruments sensitive to infrared, ultraviolet, and sub-millimeter wavelengths search for subtle signatures of dust, gas, or debris. These measurements refine models and help narrow down possibilities. One promising avenue involves studying polarization. Dust particles can polarize light in specific ways. If future dimming events show strong polarization changes, researchers could learn more about the size and composition of the material passing in front of the star. This technique has already provided hints, but more data are required. Another approach involves radial velocity measurements. These detect the slight wobble of a star caused by orbiting objects. If large fragments or unseen planets influence Tabby's star, they might leave faint signals. So far, the results have been subtle and inconclusive. But ongoing observations could reveal hidden dynamics within the system. Ultimately, the mystery may hinge on a combination of factors. Stars are complex, and their surroundings evolve over time. A mixture of dust, debris, and orbital dynamics might be shaping the strange light curve. Science often progresses by assembling pieces that at first seem unrelated. What makes the mystery compelling is not just the unusual data, but what it represents. It illustrates how little is truly known about the full diversity of stellar behavior. It shows how anomalies can challenge assumptions and open new paths of inquiry. It demonstrates that even with advanced telescopes and sophisticated models, the universe still holds surprises. Tabby's star reminds us that cosmic mysteries are not always found in distant galaxies or extreme environments. Sometimes they appear in ordinary-looking stars, hiding secrets in the fine details of flickering light. The story remains unfinished, and each new observation carries the potential to shift understanding. The study of Tabby's star will continue for years to come, guided by curiosity, precision, and the pursuit of truthful explanations. As new instruments arrive and more data accumulate, the puzzle will gradually unfold. Whether the answer lies in dust, debris, orbital mechanics, or something yet unimagined, the mystery serves as a powerful reminder of how much there is still to learn in the cosmos. For now, Tabby's star stands as one of the most intriguing enigmas in the Milky Way. It challenges theories, invites questions, and symbolizes the enduring human drive to explore the unknown. The light that flickers across the void continues to speak, and scientists continue to listen, searching patiently for the patterns hidden within its mysterious glow.